Welcome, Math 13 students. I have part 2 of my lecture on section 2.1, working with frequency distributions. Please follow me over to my PowerPoint and we'll go through our presentation. There we go. Get the slideshow going. There we go. All right. Chapter 2. Section 2.1, frequency distributions. We're going to take a look at some patterns today. Outline. In this presentation, we will explore patterns and distributions and introduce the normal distribution. Definition. The normal distribution is a frequency distribution such that number one, the counts start low, then increase to 1 or 2 high counts, and then decrease to a low count. And 2, the distribution is approximately symmetric. Here's an example. IQ, or intelligence quotient, measurements have been around for about 75 years. The most common scale centers around an IQ of about 100. Here are some data on IQ for a sample of students. And again, we have our data in table form. The left column is IQ scores. We have 1, 2, 3, 4, 5 classes. They go from a low of 75 to a high of 124. And then we have in the right column our frequency counts. And you can see them 8, 24, 36, 21, and 5. We want to verify that the frequencies start low, reach some sort of high point in the middle, and then go back down to a low point, and that it's approximately symmetric. Nature is messy, she'll never be exactly symmetric. So if we take a look at that data, starts with a frequency count of 8, ramps up to 36, that's a high point somewhere around the middle, give or take, drops back down 21, and then finishes off at a low of 5. And you can see that that pattern of low, high, low, and the symmetry is really, really supported there in that frequency count. So yes, this distribution is approximately normal. We can make that statement. I'll be asking you to judge, and these are the kind of things that you'll need to take into account. Here's another example. We're going to use the data on shoe size, and we're going to try to determine if the data approximate a normal distribution. So we're going to verify those requirements again. If I take a look at my frequency counts, I see a high of 78 or maybe 81, 50, 56, 27. This one is a little bit more spread out. I'm not really seeing a single 1 or 2 high points sort of detail in the middle. The highest frequency is in the shoe size of 7.5 with a frequency of 81. And it's kind of all around the range there. So I would have to say, in my opinion, that this data set does not approximate a normal distribution. Here's another example. This one isn't about normal distributions, it's about data itself. We have a table that will show the frequency distribution of weights and some randomly selected pennies. There's going to be a gap in the data. On the left side, you've got the weights in grams, and on the right side, you've got frequencies. If you take a look at that data, 3 of those classes in the middle have a frequency of 0. Why might there be a gap? There's a couple of reasons why there might be a gap. Here again, what I would be looking for if I asked you a question like this is a cogent reply. There's not necessarily one single correct reply. Well, there may be missing data. It's certainly possible that those coins for some reason might have been excluded from the sample. Hard to say. Those coins that weigh that amount in the middle. But if there's a random selection of coins being made, that seems to be an unlikely occurrence. Now, here's something else that you probably didn't know, and I certainly didn't know until I taught this class. Well, I would really wonder if all pennies are the same. Are they all made the same? Are they made with the same ingredients over the course of time? How have things changed? What goes on there? Well, before 1983, 95% copper and 5% zinc. That's what made up our coins, our pennies. After 1983, copper was expensive enough that, and pennies were honestly not worth that much, that it was only 2.5% copper and, well, 97.5% zinc. So you can see things really flip-flop there. So they're mostly zinc after 1983. And that certainly might affect the weight. I don't know if it makes them lighter or heavier, but it's really clear to me that those coins might possibly be coming from two completely different populations. So when there are gaps in data, we want to consider that the presence of gaps can show that the data might be from two or more different populations. But we've got to be careful. No gaps does not mean a single population. So you got to take that with a grain of salt. No gaps doesn't mean one, but if there is a gap, it might mean two or more. In summary, in this presentation, we have explored the use of pattern in distributions and introduced the normal distribution. I am now at the end of this particular presentation, and I will stop my sharing and say goodbye. I'll have more of these as the semester goes on. They're going to be tied to your PowerPoint presentations, and this, along with the material in your shell, hopefully will help you address the actual problem sets that you have. Thank you. Goodbye.